Morning, everyone. I think I'll just use this. You can hear me well, right?
Jared, you good?
1, 2. All right. So this is a talk about various obstacles that we came across while developing Linux container technologies, and the way we solved it, the way we succeeded, the ways that we failed, and so on. This is all sort of more low-level stuff, mostly kernel stuff. So I'm not talking about orchestration, I'm not talking about PaaS, I'm talking about mostly the underlying technologies, the ones that enable stuff like Docker or CoreOS. So my affiliations are I work for Odin, which used to be known as Parallels before last month, and they rebranded. And the projects I'm working on are OpenVZ, Virtualization containers, and CRIU, which is checkpoint restore in user space. Both projects are open source, both projects are for Linux. And the first problem I want to start with is the problem of doing effective virtualization. And by virtualization here, we mean partitioning, a way to divide a big server into multiple smaller ones. A historical way of doing that was using hardware capabilities. Back in 60s, as Jeff was talking about here yesterday, they have big mainframes, and universities can only afford 1 or 2 such machines. And a university is big, and there are many users. So the way for this machine to be used by many different people was to partition one physical piece into multiple smaller ones, and it was done mostly in hardware. And the modern way of doing that, or let's say used to be, is virtual machines, because current CPUs are fast and you can afford spending a lot of resources for doing virtual machines, which is basically emulation of hardware, give or take. And the problem is performance overhead. Because then you virtualize things, then you run virtual machine, you need to spend a lot of cycles, a lot of CPU cycles, a lot of power on doing just that virtualization. The partial solution to that is vendors like Intel and AMD, they provide some hardware support. It's like Intel VT technology to cut the corners and do it in a slightly more effective way. But still the overhead is pretty big of virtual machines. And the solution here is, I mean, it's sort of obvious. It's hidden in this conference name. The solution is to isolate, solution is isolation. What containers are doing is basically you have one single piece of hardware and one single kernel, and on top of that you run multiple isolated user space instances called containers nowadays. So on the usual system, all the processes, they form a tree and they see each other, and then they share common files. They can send signals to other processes. They share the common network stack, memory, there's a common set of users, everything. So the idea of containers to make all those resources private. And this idea comes a long way back. There was one historical way to make those resources private, some of those resources, and this is truth. That I think it's from like 1878. Root appears in Unix, and it allows some process to have its own files, not shared with the rest of the system. And that idea was used to run some services that might be compromised, for example. And if you run something inside that root, if you compromise it, you only see your own files, but not the whole system files. So this is sort of the protection. But that root is basically a sort of ancient container. Of course, it's not enough. It's just the file system. There is much more to it than just the file system. So in modern Linux kernel, as well as Solaris, AX, and nowadays even Windows is doing that. In Linux, we call that namespaces. So basically, we implemented something in the Linux kernel, something similar to root, but for different things. First of all, there's a PID namespace that makes it possible for you to have your own process tree, not shared with the rest of the system, so you can hide your processes from others. Then there is a network namespace, and the network namespace means you have your own network devices, IP addresses, routing tables, firewall rules, network caches, everything that when you think of networking on the server, everything that's networking, it can be separated into private network namespace. Then there are others like IPC namespace that takes care about shared, not shared with the rest of the system, semaphores, message queues. And there is a mount namespace, which is sort of like root on steroids with some added features. Then there is a user namespace that makes you possible to have your own UIDs, group IDs, and so on. All that can be enabled in the kernel. You call the clone system call with clone new whatever flags, like clone UNS, clone new PDNS. This is the way you employ that. And with all those namespaces and root, or mount namespace instead of root, you can have container. So you spawn a new process into its own private namespace. You don't see any others. You're now isolated. The next problem that comes with it is it's still the same kernel. It's still the same piece of hardware. And all those containers, while being private, they still share the common set of resources, and those resources are finite. CPU, RAM, disk, and a lot of other stuff you probably wouldn't think about. And the problem here is you need to distribute those finite set of resources between various containers in some efficient manner, so every container can have its own share. And you also need denial of service prevention, so those containers that not stepping on each other toes. So if someone runs a fork bomb inside the containers, other containers shouldn't be affected. So that's a problem of like isolation. You also need priorities. You want to have high priority container, low priority container. You need some SLA, service level agreements. You want some guarantees, basically. And there are a lot of approaches to that. So these are containers. And you need to have those walls in between. One solution that we did before, and it's still used nowadays, is OpenVZ resource controls. And we have a few things in the kernel for the resource management stuff. First of all is we have so-called user bin counters, which is per container set of about 20 different parameters that you can control on per container basis. The parameters are like user memory, kernel memory, number of open files, number of processes, various memory related things like size of network buffers, which can also be abused. And therefore you have to control it. The other thing is the hierarchical CPU scheduler that schedules on a that distributes CPU time between containers first, and then inside the container it distributes the CPU time between tasks in that container. Without the hierarchical CPU scheduler, the more processes container has, the more CPU it gets. And it's, of course, it's not fair. So we need to schedule on a container, between containers first, and then within the container. The other thing, since containers share the common file system, and basically a container file system is just a directory on the host, you need to have these quotas per directory. And that was usually not available from most of the file systems in Linux. So we have to implement the per container disk quotas. It's basically per directory disk quotas. And finally, this I/O priority and I/O bandwidth limit, which is also per container. So you can say no more than 3 megabytes per second for this container. Otherwise, they might abuse the I/O and trash the I/O subsystem. One thing that I'm not mentioning here is network priorities, but this was the only area of Linux that was good enough, so we didn't do anything in there. It was all done before us. The network stack in Linux is pretty good, and it supports all stuff like limiting prioritization and all that. So we're just using the existing stuff. Everything else we have to redo or develop. Good thing about all this stuff, it's all dynamic, so you can resize everything runtime. You need more memory, you resize it. You need more CPU, you resize it. You need less CPU, you need to, put the container into the corner. You can do that too. The bad thing about this, it's pretty complicated to set up. As I said, like 20 parameters for user bin counters, they're all interdependent, and our users were all like that. Really, really hard to configure. What we did is we wrote a book, a whole book about user bin counters. It's about 200 pages, explaining all the gory details about that. But it was still not enough. We ended up with next generation resource management, and it was called VSwap. And this is what we use nowadays. Basically, all those 20 parameters can be boiled down to two things: amount of RAM and amount of swap per container. In addition to that, there are also CPU limits, CPU priorities, I/O limits, but that is not hard to grasp. RAM and swap are also, seems natural. You don't have to explain what it means to give container that amount of RAM and that amount of swap. And for network buffers, it's a different thing. You have to explain there are TCP receive buffers, TCP send buffers, and all the different things. So this makes it simple. Other parameters, they still exist, and you can still use those, but they are becoming optional now. And one good thing about this, that the swap you give into a container is not the real swap, but a virtual one, What it means is if container is going over the RAM limits, we put some of its RAM into swap cache, and swap cache is in RAM 2. So no disk I/O is happening if it's not necessary. And only if there is a global RAM shortage, the actual swap is occurring. Also, when the container is going over its RAM limits, we artificially delay it, so it feels like it's swapping, although in reality it's not. We sort of punishing the container for going over its RAM limits, or we emulate the effect of the real swap. So this stuff is currently only available in the OpenVZ kernel. It still haven't been ported upstream. What we have in upstream is a bit different. Google were using containers for about 10 years, I guess, and they had the same problems of resource management. And they took one mechanism that was written by Silicon Graphics, I believe, and the mechanism was called CPU sets. It basically gave a way for groups of processes to be bound to groups of CPUs. And cgroup was a further development of that mechanism. It's just basically they generalized it so it became possible to group sets of processes for applying various resource controllers to those groups. I mean, in Unix, in Linux, traditional Linux, all the resource limits are usually per process, per single process. And the traditional way to control that resources is the U limit. You can set like limit RAM for the process, limit number of open files, but all these limits are per process. And the modern world is we don't deal with processes, we deal with process groups. With or without the container, each service that you run is usually a set of processes. Like MySQL or Apache is a set of processes. And it doesn't really make sense to apply limits to single processes. We need process groups. So cgroups is just a mechanism to group the processes. On top of that, there are controllers that you can apply to those sets. And the controllers are like block I/O, CPU, devices, like which devices you give to those groups. And then there is an interesting controller that is called freezer. It can freeze this group of processes, so it won't run. Then there's a memory controller and a few network controllers and so on. Now, these cgroups are orthogonal to namespaces. You can use namespaces to create containers. You can use cgroups to control groups of processes. But then you apply both cgroups and namespaces, you get the container in its modern sense. It's still a work in progress. Like, we would like to contribute our VSwap technology to upstream. We haven't done it yet. We just finished adding the kernel memory controller. Because if you think about it, if you think about the processes running on the system, they allocate some memory directly, like doing malloc in C, but they also allocate some memory indirectly in the kernel. Like when you fork a new process, there's some amount of kernel memory allocated for that. So it's not that you are allocating it, it's the kernel allocating it on behalf of you. When you send a network packet, some memory is allocated in the kernel, and it's all done indirectly, but it still needs to be controlled to prevent the bad things from happening, to prevent the denial of service attacks and so on. So for that, you also need to control the kernel memory allocated on behalf of the user space processes. And this is what KMM controller does. so it stops running. But it's not stopped in the traditional sense. It just sits there. It's just not running. So we freeze the container, and then we dump the complete state of in memory of the processes from that container. We dump all this to a file on disk. Then we copy that dump file. It's like a snapshot of the in-memory state. We copy that dump file over to the destination server, and when we undump it from there into RAM, basically recreating all those processes, I don't know, network buffers, connections, open files, everything that we had on the source server. And then we unfreeze, and it continues to run as it were, just on a different server. So this is what live migration looks like. Of course, it's a huge RAM. The dump file is huge, and it takes a lot of time to dump, copy, and undump. A long time means usually seconds, but it might be still, if your SQL query should run in a few microseconds, and when suddenly it runs in seconds, it might be a problem. So one way to optimize this process, we're trying to optimize the time that when the container is frozen. One way to optimize it is use network swap device. What we would do in this case is we dump some minimal memory, like the minimum needed memory, and we lock the rest of the memory on the source. Then we copy that minimal dump and restore that minimal stuff and mark all the other pages that are not there as swapped out pages. And then we provide a network swap device. Source server RAM acts as a network swap device for this container. And we unfreeze, and it starts to run, and it hits those pages that are not there, and those pages are then brought in from the source over the network. That way, we can migrate way faster. And when we preventively migrate all the rest of the RAM and kill it on the source. And this is very useful. This works. You can bring the frozen time down from seconds to sub-seconds with this technology. But there is a big problem with that. The problem is there is no way to roll back. What it means is when we are in the state, when we have migrated the container and it's already running on the destination system, and we swap in things in the rest of the RAM, we swap the rest of the RAM in. If the network connection breaks at this point, we are doomed. There is no way to fix this situation because it's already running here on the destination, but some pages are missing and we can't get them because of the broken network connection. We have everything on source, but as it's already running on the destination, we can't go back. So this is the problem with this particular approach, and we figured it the hard way. I mean, it was all done, implemented, and it was all good. But when we started hitting that situation of the broken network connections, and you basically ruin the container. If the network connection is broken, you ruin everything. And our users were complaining a lot. So we redeveloped everything by doing iterative RAM migration. This is sort of the same thing, but with this scenario, we can do rollback at any time. Basically, what it does is migrates the RAM before, not after. So what we do is we have the in-kernel memory, in-kernel mechanism to track modified pages. And we ask the kernel to turn this on and to track the pages in RAM that are modified for us. And then we copy all the memory to the destination system while our container is still running, up and running. We copy all the memory over when they ask the kernel which pages were modified, and we copy those modified pages again. And we do it again and again and again, iteratively, a few times, maybe up to 10 times. When there is, we do that copy, 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 and at some point we think that's enough, and it's time to freeze the container. We freeze the container, we do last copy, and when we unfreeze it. So this way, if anything goes wrong, we can stop the migration and resume the container on the source. We can roll back anytime. When the container is up and running on the destination, all the memory is there, it's all good, we can kill it on the source. We no longer need to roll back. So unlike the network swap, this iterative RAM is, let's say, unbreakable or more unbreakable. So let me go to the next problem that we have. The problem is pretty common, and it's not just for us. The problem is we developed OpenVZ containers separately, like in a closed room full of developers. We were doing that. We were releasing our stuff as precompiled kernels, or sold it, or just was giving it away, but it was not upstream to the mainline Linux kernel. And this is what other companies did a lot too. Like IBM had lots of Linux projects. What they did is they have good engineers, they develop some technology, and we test it, they document it, it's all good, it's all ready, and then they bring it on the plate and say, okay, upstream guys, take this. And upstream guys don't want to. They don't want to because there's nothing to develop, and they don't like stuff that it's completed. They need to work on that. So this is the photo from my yesterday's presentation. When you try to upstream something, this is what happens a lot of times. So yeah, this big bear is Linux kernel subsystem maintainer, for example. So you have lots of good patches, you send it upstream, and they're rejected. They say like, we're not interested, or they say, this is not the way it should be implemented. One solution, but we still want it upstream. We still want everyone to benefit from the technology, and we want it in the upstream kernel. One way to fix this problem is to rewrite it from scratch. Basically, this is what we did. For example, our user bean counters were never accepted, but in cgroups and various controllers appeared in the upstream kernel. So we were working on that controllers to replace our user bean counters with some of those controllers. Same happened with the process ID namespace. We did 2 iterations. We rewrote it from scratch, then IBM also rewrote it from scratch, and neither got accepted. And then we rewrote it from scratch once again, and it finally got accepted. Network namespace was written from scratch, and it's a pretty huge thing. I think it's about 500 patches. It's a pretty big thing. And it works this way. It takes a lot of resources, takes a lot of engineers, takes a lot of sleepless nights, but it works. But this is not the only way to get something upstream. And there is yet another way. Other big technology that we have is checkpoint restore, which is used for live migration, as I explained earlier. And we tried really hard to merge this to the upstream kernel. But what checkpoint restore does, we have it in the kernel. It basically takes care about every subsystem, everything that kernel knows about. We need to be able to checkpoint it into the dump file and restore it, like processes, open files, network connections, buffers, whatever else is there, shared memory, semaphores, I don't know, signals, lots of stuff. So we tried merging this into upstream Linux kernel, and no one wanted to see our code in there because it infiltrates each and every subsystem in the kernel except maybe for drivers. And no single maintainer wanted that extra crap in their code. And there were other people who were trying to do the same. They had their own implementation of in-kernel checkpoint restore. I know a person who spent 3 years of his life trying to merge this to the upstream kernel, and he failed as well. So we are not the only one who failed. Yeah, it's good to be in a loser's company if you're not the only loser. So we were not able to put it into the kernel, and we circumvented the system by re-implemented it in user space. If we can't do it in the kernel, let's do it in user space. It was a pretty crazy idea. The first time I heard about it, I say, it's not going to work. You're totally crazy. Please work on something else and forget about that. And this was actually the sort of, we got the same reaction from the upstream kernel developers too. They were saying something like, the project bought various mad people who trying to do things that are not going to work, but let them try. And they specifically asked us to have all this, well, we can do it in user space, but there's still some things needed from the kernel, here and there. Mostly the idea is this, everything, I mean, not everything, a lot of stuff, you can get a lot of knowledge about the processes running by looking into /proc file system. You can get the PIDs, open files, and so on. You can get the network connections. So theoretically, there is a way to get it, all that information, and then try to recreate it on a different system. This is the checkpoint and restore. Practically, some things were missing, and we need to add some stuff, bits and pieces here and there in the kernel. But it was pretty minimal. With about 150 patches, we achieved everything. And those patches, they specifically asked us, they said, it's not going to work, but we'll give you guys a try. But please put it all into ifdefs so we can cut this crap out. Well, when we will realize, then we will realize it's not working. And then later they realized, and we realized, it is working. So the project is called CRIU, Checkpoint Restore in User Space. And I think we achieved our goals. It is upstreamed. It's mostly in user space. We can't get it into the kernel. The kernel part is about 150 patches, I said. Currently, CRIU tools are at version 1.6. Google and other guys are using us. LXC and Docker are using us. Recently, I think it was Docker 1.5 that got Docker checkpoint and Docker restore. And underneath that, it uses this CRIU thing. And on top of that, we have a separate project called phole that takes care about live migration. Because CRIU is only about checkpoint and restore. And that phole, there's a thing on top of that that cares about live migration. And this is our kernel patch statistics, specifically for CRIU project. There's not a lot of patches. As you can see, we merged most of it to kernel 3.10 or so. And currently, we have only 1 or 2 patches per kernel release. mostly fixing some things, and we have 2 patches pending. Much stuff. So this is the way to merge something by not doing it. Yeah, and I believe this is the final problem I'm going to talk about. This is the problem of common file system between containers. We also realized it the hard way. Traditionally, we were using truth for containers, and when we found out that many containers, they shared the common file system, they shared the common file system journal, and if you do a lot of metadata operations, like you truncate a file by 1 byte and you do it a million times, the journal becomes contented, file system journal. And it's a bottleneck, and it breaks the isolation between containers, because one bad container can do this bad thing and all the other containers will suffer, leading to seconds of delays doing I/O. And other problems are no sub3 disk quota that we had to rewrite, no snapshots, and there are some other minor things like file system is the same for containers, so file system properties like block size are the same for containers, and this might be not what you want. So that true thing that was a solution early now became a problem. One way to solve this is use LVM, basically have your own block device and your own file system for every container. The problem is it only works locally on top of the local block device, so you can't do some network storage. And it's really hard to manage, like you have a partition, LVM partition on this disk, how do you migrate it to a different disk? It's really a hard thing to do. And then with LVM, there is no thing provisioning, meaning if you want 10 gigabytes for your container, you have to allocate those 10 gigabytes in advance. So other solution would be to use a loop device that's available, loop block device that's available in the kernel. But this is pretty inefficient because everything is cached in the kernel in 2 places, like wasting lots of RAM. Then there is also no thin provisioning, and there's very, very limited feature set of the loop device. The loop device is what you usually use to mount an ISO image, that loop device. So one good solution to this is use ZFS and ZVol technology that came from Sun. Has a lot of good features. It has thin provisioning. You can have file system in a file with ZVol. You can do deduplication. You can use send receive to migrate the data over the network in a very efficient way, similar to the way we migrate the memory. But ZFS licensing is not compatible with the Linux kernel licensing, so you have to ask your users to install it. You can't really distribute it. And Linux port is, I think, is still not mature enough. It works very well on Solaris. It doesn't work as good on Linux. And in 2008, it just was not available at the time. So we ended up writing something called ploop or ploop, which is same as block device, but with lots of bells and whistles. Basically, it's a modular design. You have the lower level, which is image format. It's upper level, the image format. You can do things like QCOW2 or other formats, or you can have the plain format. And then on the bottom level, you have various I/O backends, so you can write on the local file system, or you can write to NFS in a very efficient way, or you can do something totally in the user space and have an I/O backend that combines this ploop file from whatever you have in there. And it supports online resize, both growing and shrinking, even if file system doesn't support it. We have some features like instant live snapshot, and facilitate to make live migration faster, similar to ZFS, send and receive. So this ploop thing is only available in the OpenVZ kernel for now. We are now adding QCOW2 backend support for it, and I hope that we'll be able to upstream this technology as well. That's pretty much it. Here is my email and Twitter account, and if you have some questions, please reach out. Do we have time for a couple of questions?
Sure, 5 minutes. Absolutely.
Okay, fire up. Yeah.
Hi. So you did mention how the migration happens for the network stack. And so what are some of the big challenges that you faced in live operation when that kind of thing happens? And then you have a network being short out, so you're not able to reach the other side.
The biggest problem is TCP is pretty complicated. You probably know that it's like a state machine in the kernel, and you have to sort of copy all that state, recreate it, the existing connections, being it accepted or in progress, you have to recreate it on a different system. And the way we implemented that in CRIU is we use a special mode for the sockets. It's called repair mode. You put this TCP socket into repair mode, and then you call connect on that. Usually, if you call connect, that means the packets are going in and out, and you send SYN, the other guy send ACK, and so on. In this case, if your put socket in repair mode, you call connect, it just makes the socket like it marks it as connected and doesn't do anything. So this is the way we recreate it. Also, if there is a network buffer which is not empty, you copy that buffer and you put it there, and if the socket is that repair state, it just puts the data in there, but it doesn't send it yet. So this is the way we copy the network buffers. It's pretty complicated, and I think we still haven't upstream migrating of the non-established TCP connection. But that happens very rarely. I mean, it's usually either established or not. And currently we have the patch, but it's not upstreamed yet. It's pretty complicated thing. I mean, for TCP, for UDP, it's a bit simpler. And the way we actually do live migration is when you freeze the container, you start dropping the packets. If it's UDP, it's okay. It's supposed to be dropped sometimes. If it's TCP, the sending side will not get a ACK from us, and it will resend. And once we have migrated, we send the ARP announce saying like, hey, this IP is now here. And the sending side will resend everything, and we recreate it from there. So this is roughly the way it works. Okay.
And let's do that again. Wow. Better.
Thanks so much. Oh, any more questions?
No, no. Oh, you owe the hand. I saw it. No, no. He saw me at the front. Well, thank you very much, Kir.